Now we're going to take a look at another quantity that's associated with a square matrix, right? So we previously looked at the inverse of a square matrix, and we've seen how at the very basic level, inverses can be used to solve certain types of matrix equations. Now what we're going to look at is the determinant, which in some level, when you look at it, you might think it's very different from the inverse, but actually there's a deep connection between the two, right? And we will at some point explore that connection. But let's first, define what a determinant is, introduce some notation, and then go about defining how we find the determinant, and that will be dependent on the size of the matrix, like the dimensions, right? So let's start. So a determinant, right, is a number, and that's all it is. It's a number associated with or derived from, that's another way you can think about it. So it's associated with a square matrix, right? So for instance, let's talk about the notation for a little bit. So if we have an n by n matrix A, then we define, or we denote, I should say, the determinant of A in two ways, right? You could denote it like this, and that's kind of I guess, a reasonable way to denote it, just by abbreviating the word DET, right? Also, we can use what appears to be absolute value bars, but in the context of a square matrix, it's these absolute value bars, or these vertical bars, are interpreted as the determinant, right? So either one of these notations, and we will use them interchangeably, right? Now, as far as how we find a determinant, well, what we're going to do is go up kind of incrementally from the simplest or smallest of matrices, and eventually be able to compute a determinant for any dimension square matrix, right, in principle. So the first case is when we have a 1 by 1. And a 1 by 1, it might seem like a trivial thing to do, but that's considered a 1 by 1 matrix. In fact, let me call this, let me do this and call this A. So 1 by 1 matrix, let's say that's A. Well, by the way we define the determinant of this matrix, it's simply the number A1. So the determinant of this matrix is simply A1, 1, right? So for the 1 by 1, it's whatever the entry is, and there's a single entry in a 1 by 1 matrix. If it's a 2 by 2, right, so if it looks like this, so A1, 1, A1, 2, A2, 1, A2, 2, then its determinant, right, so you can write it like that, or if you want to write it like that, this number, the way we compute it, is by doing a familiar operation. We're going to multiply the elements on the main diagonal, multiply the elements on the off diagonal, and subtract them. So it's going to be A11 times A22 minus A12 times A21, right? And if you notice, this was that special calculation that we did while computing the inverse of a 2 by 2 matrix. And as I said, there is a relationship between what we've done with the inverse and what we're currently doing with the determinant, right? So that's what it looks like for the 2 by 2. And just as a quick example, right? So as an example of this fact, if A is 1/2, -3, 8, 16, so if that's our matrix, then its determinant, so the determinant of A is 1/2 times 16 minus -3 times 8, right? So we're going to end up with, what do we have there? So 8 plus 24 for a value of 32, right? So this is the number that we're calling the determinant that's associated with this matrix. And at least what we've seen so far is that this number allows us to find the inverse of a 2 by 2. In general, if we can do it for an n by n, you would hope that there's a way that maybe it could help us find the inverse of larger square matrices. And time will tell. All right. So now, what about the 3 by 3 or higher? Well, for the 3 by 3, right, or higher, it's not so easy to write it down. I mean, we could write down something for the 3 by 3, but if you try to continue that process, it just gets completely out of hand. It just becomes completely unwieldy, and it's not an efficient way to write down the determinant for the larger matrices. So we're going to take a slightly different approach and define a few quantities that are recursive in nature, right? And you'll see what I mean, but those quantities will help us define the determinant for higher dimensional matrices, right? So the first thing we're going to define is the concept of a minor, right? So a minor, right, is the determinant, right, of the submatrix, right, remaining after removing, so after removing or deleting a row and column from our matrix, right? So removing a row and a column from a matrix. And again, this is all for square matrices, and we're going to call that a minor. So we need the notation for this, and the notation for a minor, we use a uppercase M. And now, since it's talking about removing a row or a column, then how many? Well, or which ones? How do we indicate which row or which column to remove? Well, we're going to use the subscript ij like we've used before. And again, this is basically saying that we're going to use this notation to represent the minor, right, of the submatrix, or I should just say not the minor of the submatrix, but the minor of the, let's say, ij entry that's in, with the row I and column j removed, right? So with row I and column j removed, right? So that's a minor. The other thing that we need to define in order to talk about the determinants of these larger matrices is something called a cofactor. So a cofactor, and we're going to use uppercase C, right? And I'll just use this phrase, is called a signed, S-I-G-N-E-D, minor. Right, and what's that saying is that some of the minors and cofactors are going to be the same sign, and then others are going to be the opposite sign, right? But the numerical value will be the same, but it's either going to be a positive or negative of that, right? And that's what we call a cofactor. How is it defined more precisely? And how is it denoted? Well, it's like this. So it's C, and then with the subscripts, again, I, J. That's the notation for the IJ cofactor, and this is how it's defined. It's negative 1 raised to the power I plus j, and then you multiply by the corresponding minor. So the minor IJ. And this is why it's called a signed minor. It basically is, once you know the minor for a particular entry, then you can find the cofactor by multiplying by this factor of negative 1 raised to the power I plus j, right? Okay, so let's just do a couple illustrations of this before we define the determinant of a 3 by 3 or higher matrix, because that definition will involve these cofactors. So we have to know how to find the cofactors before we can use that approach in our definition. All right. So what I'm going to do, let's start with a 3 by 3 and just compute a couple of the minors. I won't compute all of them, but just some. So here's an example. So let's say we have the matrix 2, negative 3, 5, 1, 1, 8, 2, 2, 7. Right? So there's our 3 by 3 matrix. Now, because, again, the minor is with respect to a specific entry in the matrix, technically there are 9 minors that we can compute. Right? There are 9 of them we could compute. I am just going to compute a few and then also compute a few of the associated cofactors. So let's start with something like M11. Right? So M11. Well, what it says is I have to remove row 1 and column 1 from my matrix, right? So let me write down the original matrix. Oh, in fact, let me write something before. So it says the minor is defined as the determinant of the submatrix that's formed by removing a certain row or column. So it's the determinant of what we're going to write down here. Right, so there's our full matrix. But now, if I remove, and that's what the subscripts are telling me, remove row 1 and remove column 1. So I'm just going to strike through them. So remove row 1, remove column 1, and then take the determinant of this, what we call a submatrix. It's like a matrix within a larger matrix. So when we remove row 1 and column 1, we're left with the submatrix 1, 8, 2, 7. But now that's a 2 by 2, and we have a definition for the 2 by 2 determinant. So then, again, in fact, let me write it like this so you can see another way of writing the determinant. You can do your vertical bars, put the numbers in the same way like we put in a matrix, but with the vertical bars now, it indicates a determinant. So don't confuse the vertical bars with the brackets. The brackets represent a matrix. The vertical bars in this context indicate a determinant. And now by definition, this is 1 times 7 minus 8 times 2. So the minor, right, the 1, 1 minor for this matrix is the number -9, right? There it is. Now, if I wanted to find the associated cofactor with this, so I would do this. The cofactor of the 1, 1 entry of this matrix will be -1, and then the exponent is going to be the sum of the row and column indices. So 1 plus 1, and then times the corresponding minor, right? Now, when I do this, what I end up with is negative 1 squared and then times the negative 9. So in this case, because the exponent comes out to be a positive number, right? Then you end up, I'm sorry, not a positive number, well, it is positive, but the fact that it's an even number, it means that this simplifies to a 1. So you end up with 1 times negative 9. So in this case, the cofactor and the minor are exactly the same, right? Now, if we let's look at another example. So let's take the minor 2, 3, right? Well, what is that one? Well, again, it's going to be a determinant. Now you start with the original matrix: 2, negative 3, 5, 1, 1, 8, 2, 2, 7. Now to find the 2, 3 minor, remove row 2 and remove column 3 and find the determinant of the submatrix that remains. The submatrix that remains is going to be 2, negative 3, 2, 2. And again, I'm using the vertical bars to indicate that we now take the determinant of this, right? And then, so using our formula, it's 2 times 2, that's 4, minus negative 3 times 2, that's negative 6, for a value of 10, right? Now let's find the corresponding cofactor. So C23, by definition is negative 1. Now it's going to be raised to the power of your I plus j, and then that's times the corresponding minor, 2 comma 3. Well, now we have negative 1 to the 5th power. Because that power is odd, it's going to be the opposite of the minor, right? Because you're going to end up having negative 1 times 10, so negative 10. And this is what we mean by a signed minor. So depending on the parity, and the parity is referring in this case if something is even or odd. So if the sum of I plus j is odd, then the cofactor is going to be the opposite of the minor. If your I plus j is even, then your cofactor is going to be identical to the minor, right? Okay, so that's the idea of minors and cofactors. So how does this help us find the determinant of a matrix? So we're going to write down now what we can do in principle to compute the determinant of a 3 by 3 or a 4 by 4 or a 5 by 5. Now I say in principle because even though we will write down this definition, it is not a very efficient definition for really large matrices. So we'll be able to come up with a more efficient way of doing this, but this is a starting point, right? And in fact, this definition that I'm about to give is the one that you may have used in other courses where determinants are just like little tools that you need to compute other things, right? So the determinant, right, of an n by n matrix, so of an n by n matrix, is defined as, right? So let's write down the general n by n matrix now. So we will have our A, and then here's our matrix. So it's going to be the A11, A12, and so on to A1n, and then A21, A22, and so on to A2n, and so on to AN1, AN2, and so on down to ANN, right? So again, what we're going to write down now is, in principle, a definition for the determinant of an n by n matrix. So this is how it's defined. So DET, and what you do is you have to find the cofactors, right, for each of the entries in the first row, right? So you're going to have to take, so I'll write down a couple things and then I'll go back in and fill in other pieces to this. So the first thing you're going to have to do is compute, or again, this is what the definition states, go ahead and compute the cofactors of each of the entries in the first row. So C11, C12, dot, 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 C1n. So you compute those. Then what you do is multiply each cofactor by the element that's in that position. So A11, A12, dot, 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 A1n, and then add those all together. So plus, plus, dot, dot, plus, right? And this is the definition for a n by n matrix, right? And this is called the cofactor expansion of the determinant, right? So this definition, right, and is called the cofactor expansion, right, of the determinant of A, right? So let's kind of box that off. This is our formula, right? So we find all the cofactors of every position in the first row of our matrix, right? And we have a way now of finding those cofactors. Then we multiply each cofactor by the entry in that position, right? And then sum those products all together, all right? So let's do an example of this. So we'll start with the 3 by 3, and in that case we're going to have to compute 3 cofactors, right? Do these products and then add them all together and come up with our determinant, right? So let's do this, right? So let's say A is, and again we can write down any 3 by 3 that we want, but let's say it's 1, -2, 3, 0, 4, 2, or 3, 2, 5, -6. Alright, so there's our square matrix, and now what we want to be able to do is compute the determinant of this 3 by 3, right? Okay, so what I'm going to do, pretty much the same way we did it in our previous example, let's first compute the minor and then the corresponding cofactor and then put it all together using this definition, right? So the minor 1, 1, that is going to be, so let's do it mentally now to delete the first row and the first column. If I delete the first row, first column and the first row, I am left with 4, 3, 5, -6. So that's the sub-matrix, right, that remains after deleting a first column, first row. So, and then by definition, we have to compute its determinant, right? And that will give us the 1, 1 minor. So this, by definition, is -24, -18, so that's going to give us a -42, right? So that's our M11. Then right away we can find C11, and that is -1 raised to the power 2, because it's I plus j, times our minor of -42. But again, because this -1 is raised to an even power, that is equal to 1, and then that does not affect or change the sign of the -42, right? So let's go ahead and compute the other one. So again, and by definition, it's all the cofactors of the entries in the first row. So I have to go across M11 and then M12. Right? Now let's see what submatrix remains if I delete again the first row and now the second column. If I do that, I'm left with 0, 3, 2, negative 6. Right? So 0, 3, 2, negative 6. Well, let's use the definition for our 2 by 2 determinant. So this product is 0 and then minus 3 times 2, that's 6. So we end up with negative 6. And then we have our C12, which is going to be negative 1 raised to the third power times negative 6. And now, because our I plus j is an odd number, then the cofactor is going to be the opposite of the minor. So it's negative 1 times negative 6, which is a positive 6. All right? So we're 2/3 the way as far as computing the cofactors that's needed to apply this definition. Well, we have one more to compute, right? Because it's a 3 by 3, we have to go all the way across until we get to that third column. So let me go back up a little bit more. So our M13, now delete first row, third column. So first row, third column. That leaves the submatrix 0, 4, 2, 5. And then 0 times 5, so that's 0. And then minus 8, so that's negative 8. And then let's compute the corresponding cofactor. So that is negative 1 to the 1 plus 3 power, that's the fourth power, times the corresponding minor. And then in this case, because the sum of I plus j is even, then we end up having a cofactor that's the same sign as the minor, right? So it's negative 8. All right. And that's all we need, right? So we don't when we're computing the determinant, by using this definition, we use this cofactor expansion, right, using the elements or the entries in our first row, right? So by using this particular method to compute a 3 by 3 determinant, I need to compute, you see what we ended up doing? We ended up computing 3 2 by 2 determinants, right? So to compute the determinant of this matrix, I had to break it down and compute the determinant of these 3 submatrices. And once we have these cofactors, then we do the following, right? So again, let me write it out symbolically so you can see it, and then we'll substitute the values that we have. So by definition, the determinant of A is A11 times C11 plus A12 times C12 plus A13 times C13. Right? So do we have all, so basically we need 6 numbers. Do we have them? Well, yeah, we definitely have the A's because those are given in our matrix. And we have our C's, those are the numbers we just computed. So let's multiply and see what we have. So we have A11 is 1, so we'll have a 1 there, times C11 is negative 42, plus A12, that's negative 2, times C12, which is a 6, and then plus, as I can scroll over just a little bit, right? And then plus A13 is 3, and then times the C13 cofactor, which is negative 8. Right? So let's see, what do we have here? We have a negative 42 minus 12 minus 24. So that is what? Negative, so 42 plus 12, that's 54. Plus 24, so that's 78. So this ends up being negative 78, and that is our determinant of this particular matrix, right? Again, what does this number really mean? We will see in the future, not too distant future, the way that this particular determinant can be used, right? So again, this definition is a recursive definition because in order to figure out the determinant of a 3 by 3 matrix, we had to figure out the determinant of several 2 by 2s, right? And then in subsequent videos, we're going to see other methods that we can compute determinants with. And maybe it's not so tedious of a task, right? See you in those videos.